Good morning to everybody. Myself, I am Dr. G.P. Bhavani, Head of the Department of Chemistry. Respected guest, Dr. J. Sai Chandra. Respected Secretary, Lalit Kumar O. Jain. Respected Management, respected Principal, Dr. N. Sujata. Dear colleagues, participants, and my dear friends, very good morning to all. It's given me a great pleasure to welcome you all. Our institution, Sri Chandraprabhu Jain College, offers a wide variety of programs, both online and offline, with a main goal exploring the knowledge of the students globally. In addition to knowledge of our students, highly competitive in the today's prosperous society. First of all, I wish to appreciate to has interest in exploring the knowledge by joining our online session organized by We Can Institute the International Virtual Seminar on Chemistry 2023. I welcome our special guest, Dr. J. Sai Chandra, Assistant Professor of Chemistry, Jintu University College of Engineering, Sultanpur, Sakareddy District, Telangana. He gives the topic of presentation, growth of good quality of crystals from amino acids and amino acid based materials from nonlinear optics applications. We know nonlinear optics allow us to change the color of light beam to change its shape and space and time. The application of NLO, nonlinear optics, is wide. Some of them mapping, parametric applications and oscillations, simulated light scattering, SLS, and four-wave mixing, FWM, etc. It's a wonderful and very useful topic in our day-to-day life. Thank you, sir. Once again, all the participants, I heartily welcome all. I hope all of you will enjoy the sessions. Have a good time. I have handed over the session to Mr. De Silva, Assistant Professor in English. He give the introduction to our chief guest. Thank you, sir. Please, sir.
Okay, good morning to one and all present here. I am here to welcome our eminent guest, J. Sai Chandra, working as an Assistant Professor, Department of Chemistry, JNTUH College of Engineering, Sultanpur, Telangana. His area of research is in doped crystals of inorganic transition metal complexes and organic synthesis with indole complexes. He completed his postdoctoral fellow in 2017. He completed his PhD in the year of 2015 from Acharya Nagarjuna University. He has 25 international national publications, journal reviewer for 5 international journals and 3 memberships. He has 11 national and 3 international patents. Among them, 1 South African patent granted for the year 2023. He received various awards as Young Scientist Award from Puducherry and Best Researcher Award from Chennai. Attended short-term courses from NITTR and FIBS and workshops also towards the various country and state universities and colleges. So I welcome you, sir, for the international seminar. I'm happy to welcome you for the great event. I handed over the session to Dr. J. Sai Chandra, sir. Thank you so much.
Thank you, sir. Thank you very much, sir. And Bhavani, madam. Good morning, one
Thank
and
you,
all.
sir.
Good morning, one and all, and happy welcome to me. To all the students or the participants who are participating in this seminar, a warm welcome to all. And myself, as a topic we have given already displayed in this, is the slide is visible to all? Growth
Yes,
of
sir.
good quality.
Yes, sir.
Yes, okay, right.
Yes.
Right. Growth of good quality crystals from amino acids and amino acid based materials for nonlinear optics. And we ourselves are doing this as a research topic, and furtherly also we are going towards the future generation crystal and crystallography. And the basic topic which we can understand here from this is the doping technique. And the doping is a well chosen and widely accepted technique for incorporating the required physical properties in a bulk material, which are we are using for the technological applications. And we can see this technique which is essentially explored to modify the properties of which we are saying it as electro-optical, non-linear optical, which we can see this in the future generations. And also now we can demonstrate this metal ion dopants, which are most versatile, and we can see this modifying the properties of different compounds. And now in this topic, which we are giving here, the growth of good quality crystals from different amino acids, and from these different amino acids we have chosen here as L-histidine, which is basically doing as a good doping and which gives a good result towards this transition metal ions. And here we can see the metal amino acid interaction between this widely studied, and we can see this biological importance and clear cut description we can see in these slides. And we can see this at metal amino acid complexes which we can prepare, and we can see here as the biological activity also which can be displayed for the future generations, and the basic biological activity and the anti-cancer studies also which can be studied in the future. And we can see here we are coming to the L-histidine, the amino acid which we are taken here, as you can see it as more optically active, and which you can say alpha amino acid, so that we have chosen this amino acid as for our research oriented. I'm coming to the slide we can see, and which we can see here as an introduction of growth and characterization and an NLO optics and biological activities. And we have chosen here as five different metals, elements. We can see iron, cobalt, nickel, copper, zinc. And we can choose in this as one of this transition metal ion as manganese. We are doping, inter-doping technique, this one we are calling it as. And we can see here as with the L-histidine amino acid. But first one we can see it as iron doped with manganese ions with the amino acid L-histidine hydrochloride monohydrate. And with this doping technique, we can develop some crystal format. We can see in the further slide of images also I have represented here, and we can see. And like this, we have studied and we have representing here as cobalt, nickel, copper, and zinc. These are the five different metal ions. We can see elements which we are studying with the common element manganese and with the common amino acid, right? And here we can see some of these objectives related towards this L-histidine, and we can study moreover many of these elemental studies towards this. And we can see here that to develop amino acid complex, which we are saying it as host system, which we are naming it as, and with the diamagnetic paramagnetic impurities of transition metal ions as dopant for technological and pharmaceutical applications. So we are developing here as the diamagnetic and paramagnetic nature of a particular crystal, and while doping with the amino acid. And we are while doping with the amino acid, there is a formation of a complex. We are naming that one as transition metal complex with the help of amino acid. And here we can see to identify a suitable composition and suitable transition metal ion in L-histidine hydrochloride monohydrate system for technological applications. We can see in the applications in the next slides, right? And like this, we can see the diamagnetic host modalities, and next with the combined with the advantage of inorganic and organic molecules to obtain the semi-organic crystals for potential NLO applications. This is the main theme which we are developing here with the NLO applications. And going towards this, we can see the crystallography. The main theme of this crystallography, it plays a major role towards the coming generations. And we can see each and every metal we can develop this crystal format. And here we can see the definition of this as a crystal is made up of atoms or other microscopic particles which are arranged in periodic manner. Three-dimensional crystals have been invaluable always as constituents of ornaments for thousands of years. Nowadays, we can see many of these crystal formats in the market levels also, which we are naming it this one as the ornamental level and some of this as biological standards. We can separate these two as a part of this ornamental value. the technological applications of crystals paved a way for the development of science. We are naming it as crystallography. So now this trending topic, crystallography, which has different linear optics, the quantum electronics, optoelectronics, and different telecommunication levels we are generating here. And we can see this how the crystal growth methods have been developed. We can see many of the formats in the research oriented, we can see, and some of these are mentioned here for the crystal development. And this crystal growth development technique we can develop it as easy as possible, and we can see in the small chemistry laboratory also. Why we are naming it as the slow evaporation technique, which we can see here. I will explain you in the further slides also, which we can develop these slides with different types of amino acids. And the financial, we can see that as one as also is very lower and lower. While we have to we get it for the amino acid itself. And the metals, we can see the different metals, so we can see in the 100 to 1000 rupees of or expensive, we can see. And with this, we can see different metals can be doped with the different amino acids, right? And we can see the methods as growth of crystals from solution occurs if same degree of supersaturation or super cooling occurs in the system. And here we can see the three steps of crystallization process, and we can see that achievement of supersaturation or supercooling, and we can see the formation of crystal nuclei and successive growth of crystals to get distinct phases. And the basic crystal growth methods, as we can see the crystal growth from melt, and we can see from the solution and the evaporation technique. And these are the different techniques we can see for development of a crystal. And these takes a time duration of 1 month to 45 days duration for the development of a small layered crystal. And beyond the time duration, 45 to 60 days, the time duration, the layer formation will be developed in a sequential manner. And that layer formation we can get studied towards the different analytical growth techniques, and we can see in the next slide. And here we can see this as the crystal growth, what we have used now present in the study. We can see it as we are using this method as growth from solution for the growth of crystals. And we can see the division of two temperature levels as a low temperature and high temperature level solutions. And these crystals reform growth for the low temperature solutions, which can be subdivided into two techniques. We are naming it as slow evaporation technique, slow cooling technique, and also we have explained in the previous level as a temperature technique method, as temperature gradient method. And we are following this linear optical methods also with the nonlinear properties, which are found as optical and optoelectronic devices, which we are selecting for the analytical techniques, which lead to the development of crystals, which shows the interlattice spaces in the crystal form, whichever we have formed the crystal. And we can name that one as inorganic or organic crystal format. And here we can see some of these different wide transparency domains also we can see. But the readily available large single crystals, ability of process of crystals into thin films, easy of fabrication, non-toxic, and good environmental stability. So these are some application oriented we can see, or else we can use this, we can see what we have developed with the crystal, whichever the crystal is useful for us. And we can see it as fast optical response time, we can see. And these are some properties levels which we can observe this one, organic crystals and inorganic crystals, which differentiate two of this. And we can see each and every compound which is generating now, we can observe this type of chemical nature, and which are covalently bonded or not, which are, we can see salts composed with the charged inorganic ions. And we can see the solubility, which is solvent, which is used for the solvent and soluble. And sensitivity, we can see pH studies, which is sensible, which are the pH range of which are acidic or basic condition which can observe. And the thermal properties and crystal size, X-ray diffraction, mechanical strength. These are different property levels which we can study for a good formed crystal. And these are some inorganic origins of different already formed crystals, which we can see. This one as a potassium pentaborate as the first NLO crystal is already studied you can see, and other borates like barium, borate, lithium. Because we can see such type of references in the research oriented of the previous already done. You can see borate like barium borate, lithium borate, strontium, etc. You can see different types of crystal formats in the already studied with this NLO properties. And the crystals of this potassium dihydrogen phosphate and its homologs are mostly widely used commercial NLO materials due to their excellent UV transmission and high bifrequency and a relatively high laser damage threshold values. If we can observe this type of material as linear optics for the different types of crystals, with as we are naming it as potassium dihydrogen phosphate. This KDP crystal shows a good results towards its good results towards its NLO nature. And you can see also the KTP crystals also. We are naming it as potassium titanyl and phosphate. We can see the wide applications of wave guides, electro-optical and periodic pooling structures we can see. So these are the two techniques. Basically, there are the two dopings of crystals with the KDP and KTP. Two types which we can observe this NLO properties more and more and easier to get at. And we can see some of this as 4-dimethyl amino and methyl 4-stilzolum and tosolate. We can see it as we are naming it as and potassium NLO opticals and different types. You can see different examples here. We can see now this also we can see. And these are, we can see, amino acids. These are the basic amino acids which we can study with different streamlines. Each and every amino acid which plays a different role. And from this we can see as aqueous solutions for most pH values of amino acids, which we can see the deuterionic nature, which we can observe this. Deuterion means we can observe this as both the positive and the negative nature, and which we can be reacted and attract towards attention of this contain which infinite sequence. And we can see the tail hydrogen bonds and which play leading role in the catalytic biochemical process as NH3, ammonium plus ion, and CO minus ions. We can see different attractive natures can be observed, which we are named it as zwitterionic nature. And here in this, which serves as biomimetic nature, where due to the presence of this zwitter ionic nature, we can observe this one as biomimetic. And we are naming that one as a term for majorly for the optic level studies. And this optically active amino acids, which shows the complexes, are highly efficient for optical second harmonic generation, which are named as SHG molecules, and the properties which we can study for this such type of amino acids, which are named as zwitter ionic nature of amino acids. And this such type of nature we can observe in the elicited amino acid. And we can see this breaking of center symmetry and different streamlines we can observe here. And these are some biological role of amino acids. We can study growth of amino acid complexes with metal ions in aqueous solutions and the doping techniques, which are we are naming here as is a practice of adding impurities to a substance to very low concentration. And here we are mentioning it as 1:1 ratio of impurities. Impurities nothing but we are adding here the metal ions as elements, which we are naming it as the impurities. And this practice alerts the physical properties of substance and the transition metal ions are dopants, which modify the growth habit of crystal, and we can observe such type of shape oriented, whether it will be octahedrals or we can see different shape format of this crystal in the layer whichever adding the impurities depending on the impurity levels. And these are some NLO studies which we can observe here as the NLO studies which we can report these amino acids as alanine, diglycine, and L-arginine, different amino acid. And based on this, we can give the importance towards this amino acid as L-histidine, which we are getting towards doping now. And it is a compound of this mice study, and L-histidine, we are naming it as L-amino beta imidazole propionic acid, and is the only amino acid having imidazole side chain. We can see imidazole side chain as we can observe here. And to this imidazole side chain, the attraction of impurities takes place, and the doping can be takes place here. And these are the studies reported on different eliciting compounds. We can see this reported eliciting covered broadly and the important points of the studies, and we can see different. And now we have observing here the complexes of copper, zinc, magnesium, cobalt, and uh, mercury, and different compounds, different like this reported already in the with the analytical properties. And we can see the doping of elicitin also, elicitin hydrochloride also reported. But we ourselves are doing this with the doping of double metal transition, double transition elements. We can see. And how this is a ratio type of percentages we can observe here. The growth of different, we can see iron, cobalt, nickel, copper, zinc, and these are doped with the magnesium and manganese, and with the elicitin hydrochloride monohydrate. And this one you can see hydrochloride monohydrate crystals. We are calling it as MnHCl, and we are naming this one as the percentage levels we can see, and how much the grams and how much moles we can observe here, with the grown by adding 0.01 mole percentage of metal to it. And these are the solution of concentrated state for 2 hours with the magnetic stirrer to obtain homogeneous mixture and filtered through a Wattman filter. This is a common technique that we can observe it. And the solution can be transferred fresh 100 ml beaker and covered with porous aluminum foil before leaving it, and we are naming that one as a slow evaporation technique at room temperature, which we can say. And the different types of colored crystals are formed here in this. We can observe this one as different sizes we can mention here. And depending on this amino acid, we can observe this one as the elicitin hydrochloride monohydrate crystals. We can observe this one with different streamlines and different sizes. And the crystals which are washed with acetone and the dried dimensions, we can well know it as 12 by 10 by 4 mm. And these sizes may vary depending on the crystal formation and the duration which you are attempted. But and next we can observe this one as the characteristics and characteristic techniques. We can observe this one as which we are going to analyze the techniques which we are going to represent it. And these are the XRD spectra, EPR spectra, FTR spectra, and different UV visible proton number, mass, TGTT, and we can see thermal techniques, and we can see it as the DSE and micro hardness, chemical agent, different NLO activities and biological activities. These are different studies we can observe as we can futurely generate such type of crystal is generated for the anti-biological active studies or not. And we can observe this one as the first one, and we can see it as the development of iron doped manganese elicited hydrochloride monohydrate crystals, which are already published here. And we can see the different powder X-ray studies which we can develop here. And in this we have observed this as orthorhombic system with a space group of P212121, and we can propose that one as ions doped in particular manganese elicited hydrochloride crystals. And we can observe this one as lattice change parameters can be observed, which we can display here. We can observe this one as the comparison of basic elicited hydrochloride monocrystal, and which we can in the top we can observe this one green one as doped iron doped with manganese elicited hydrochloride crystals. And we can observe this differentiation of X-ray powder studies as variations. And in this, we can say this as one as a lattice cell parameters, which are explained here in detail with the ABC crystal lattice parameters as orthorhombic system, which can be space grouped as P212121. We can propose that one as iron, particularly doped with the manganese elicited hydrochloride crystals. So these are the values ABC parameters which we can observe as varies with the depending on the metal which are substituted. And the values suggested by the doping do not bring any major changes in the lattice cell parameters of doped crystals, and we can see that compared with that of pure L-histidine hydrochloride crystals. And we can see this one as we can see the experimental and calculated data also, which we can observe this one iron doped with manganese L-histidine hydrochloride crystals. And we have studied this type of crystal studies calculations towards all the transition metal ions. And we can see this next one as EPR studies, electroparamagnetic nature. Of we can see it as resonance studies, which we can observe this one with the magnetic behavior of zero field crystal splitting parameters of transition metal ions in the crystal studies. And based on this standard patterns, we can see manganese and the iron ions were observed in the crystal, which shows the peak observation. And we can see it as is equals to 4.2, and we can observe this such type of distorted octahedral symmetry. Octahedral symmetry, we can observe this one as which is slightly changed with the distortion, right? Changes we can observe it. And the manganese ion, which has d5 electronic configuration with 5 half-filled d electrons, which we can observe this due to the distortion of octahedral symmetry. And the resultant angular momentum, which is we can name it as zero, and the particular studies we can name it as zero field splitting studies. And the local field geometry, which we can name it as the site symmetry, and which we are naming this one as electron paramagnetic resonant spectral studies. And we can here next see the study of FTIR, which we can observe this infrared spectroscopy, which we can name it as of the peak observation of different transition metal ions, and which are doped with the side chain of L-histidine hydrochloride monohydrate crystals. And here the spectral determination we can observe here as small shifts were observed in the characteristic vibrational frequencies, which you can FTIR spectral or iron doped with manganese of when compared to the pure L-histidine hydrochloride crystals. We can observe here as shift frequencies of variations we can observe from amine as 3157 centimeter inverse of pure L-histidine hydrochloride crystal towards this doped we can observe as 3154 centimeter inverse. As for this imidazole nitrogen, for we can observe this as 1143 and towards this 1139 centimeter inverse, and carboxyl oxygen we can observe 1637 to 1633, and we observe the supporting coordination of these groups as the manganese ions, and the values which represent this as iron is completely doped in the manganese L-histidine hydrochloride crystals. And here we can see the different variations of this value, which we can see for the iron doped manganese L-histidine hydrochloride crystals. Of these values, pure L-histidine hydrochloride and iron doped, we can observe this variation of OH stretching, NH stretching, and we can see aromatic nature, and cobalt CO stretching, and we can say asymmetric bending, asymmetric stretching of CO minus, and symmetric bending of NH plus. We can see different streamlines of this FTIR, of this growth of the particular iron is completely doped in the manganese L-histidine hydrochloride crystals. And these are the different spectral parameters. We can observe this as optical observation. And optical absorption spectrum, we can see here as for Reka parameters of test correction, and we can observe this one. Iron ions in manganese L-histidine hydrochloride are calculated with DQBC of the values, which we can mention here. And the bands which we can observe is 425 and 16 nanometers. Corresponding to this, we can observe this one as A1G, 6A1G, and 4A1G, and which one can test S stage towards this ground level state. We can observe this one as shifted towards this. And D1G, ground state transitions, we can observe this. And the crystal field DQ Reka parameters and trace correction, we can observe this value as DQBC values that got varied with that of different manganese doped and iron doped. We can observe the difference of these two. And in the first one, we can observe this one as DQBC as 700, 610, and 2360. And for this, while we can see it as manganese ion with the manganese L-histidine hydrochloride, we can see it as DQ 850, 810, 2780. So we can observe these two differences. By this, we can say that one as the iron is completely doped in the manganese elicited hydrochloride crystals. The difference variation of this optical absorption spectrum varies, which shows as the iron is completely doped in that. And we can see here as a spectral determination of the optical as 6A1G towards this 4T2G ground state level as a wavelength of 725 nanometers. We can observe this one, observe calculated. We can see the two different variations of this, right? And we can see the difference of this iron ions and the manganese ions in two different variations, as DQ values can be observed in the different variations. DQ for this iron, we can see it as 700, and for this DQ of manganese ion, we can see it as 850. And the BC values also got varied, and this while doping, we can say observe this as where values are differentiated in different streams. And next, going for this proton NMR studies, which plays a key role towards this of any organic molecules or organic studies which we need to mention. And here, the proton NMR spectrum of iron ions doped with manganese elicited hydrochloride crystals are shown here in this figure. We can observe this one as the pure elicited hydrochloride resonance of this spectral determination. We can observe this one as which we can see as the iron determination as completely doped with the manganese. With the values we can see pure 4.35, iron doped we can see it as 3.98 ppm levels we can observe with this 3.47 and 3.28, and alpha and beta values, beta are hydrogens which are completely present in the pure and the iron, which will observe the difference of these two hydrogen levels of alpha and beta, and the hydrogen H2 of imidazole ring and H4 of imidazole ring. The two variations we can observe as 8.73, 8.59 and 7.48 towards 7.32. And the carbon NMR, we can see proton NMR we have studied, and this carbon NMR also we can see the delta values of different cobalt groups which are present in the NMR function. And here we can see it as the peak resonance of delta 176.86 ppm for the presence of cobalt group of side chain, and two consecutive signals of delta 139.20 and 135.21 ppm for the presence of CH groups. And for imidazole ring, we can say it as presence of CH groups which are present in the imidazole ring. We can see the eliciting structure imidazole ring. In that imidazole ring, we can see that the CH and CO function. And the peak at 119.23, and we can see it as two resonant peaks resolved. And by going towards this two different the different peaks we can observe here as we are compared with this as same with that of NMR towards this C13 also. We can see the pure 176.86, and we can see it as 172.99. We can see it as cobalt of side chain, and CH of imidazole ring and the hydrogen we can see it as 139.20 and 134.21. We can observe the variation of this, and 119 of this C of imidazole ring and CH of side chain we can observe this as different variations can be observed with this NMR technique. And coming to this mass spectral studies, also the major important stream. That means the mass which majorly determines the weight of the molecule or the complex which is formed. The complex, the previous pure eliciting hydrochloride crystal which is formed is compared to the top, we can see that one has the majorly changes towards this iron doped. And we can see the spectrum recorded towards molecular iron and plus peak is as 305 MU, and the corresponding very close to the major species. We can see it as the provision of inclusion of doped species present in the low concentration levels. If we increase the concentration levels, the crystal size may vary, and also the presence of transition metals also varies. And based on this, we can observe this mass spectral varies with a huge difference can be observed towards this pure and towards some doped. And the small variation of this variation is observed due to the presence of this. We are observing this 0.01 low concentration at, which we have present studied with this. And a small variation in this molecular weight could also be an indication that the molecular structure of this showed series of peaks that 113, 181, and 203 and 222 AMU corresponding to various fragments molecular. You can see whose intensities have gave an idea about the stabilities of the respective fragments. So these values which studies which shows the 305 highest peak recorded value, which is very, very closer towards this major species of, which we can observe this one as allicin hydrochloride crystals. And we can see this mass spectrum also represented here, which we can see here highest peak of 305.2 AMU. And these are some thermal studies which we can see. And DGDTA we are naming it as. And we can see the different variations of this DSC and the DGDTA. Of this, heating techniques can be observed. Heating by the formation of this crystal, how much temperature, up to the temperature levels, it can be managed. We can see with this melting techniques and also this as thermal studies. Different variations can be observed this DSC and DGDTA. And we can see thermogravimetric and differential thermal analysis, which we are seeing it as TGDTA, and the differential scanning calorimetric studies as used for identifying the phase transition temperatures, which varies stages of decomposition and melting points of ground crystals. So each and every ground crystal which shows as leading crystallization, that means the crystal which is formed is in a particular lattice or not, is in a particular shape or not, which is distorted, which is present or which is completely doped or not, which we need to study with this thermal studies, and which we can say it as phase transition temperature variation can be observed towards this a particular ground crystals. And for this thermal analysis, a sample we can heat it as a temperature atmosphere heating technique of 0 to 800 degrees centigrade, and at a particular heating rate of 10 degrees centigrade per minute. We observe this one as 0 degrees centigrade towards this highest of 800 degrees centigrade. And we can see is iron doped manganese eliciting crystals of first the weight loss corresponding to 4.97, which is occurred at the temperature range of 150 to 200 degrees centigrade, and which is attributed to loss of some water molecules which are present in this. Completely, the crystal formation is presence of water molecules. While applying these thermal studies, we can observe this variation as the water molecule loss will be observed by every crystal, which we can observe this at of 150 to 200 degrees centigrade. And the maximum weight loss observed in this range of 287 to 373 for the doped crystals. And for this DTA, we can see it as differential scanning calorimetry. We can see, and also this differential thermal analysis, and we can see this iron sharp endothermic peak at 200 degrees centigrade, which is attributed to removal of water from crystal lattice. And here we can see a second peak, which we can see it as 287 degrees centigrade. And we can see here as a 287 degrees centigrade as the DTA technique, and we can see the image here. At this particular ranges, we can observe this one as the first major decomposition of the melting point of iron doped and manganese eliciting hydrochloride crystals. So these are two variations which we can see particular iron is doped or not, which we can differentiate this one as a particular iron or the transition element is doped in a eliciting amino acid crystals. And here we can observe this one as a peak of 287 degrees and also the melting range of 4.97%, which we can see as a 150 to 200 degrees centigrade. These are the two variations which we can observe as the particular amino acid is doped with the transition metal or not. And we can see it as different variations also for the DSC analysis as that we can see it as iron doped with a temperature range of 110 to 310 degrees centigrade and display the same characteristics which we can observe this in the TG and DTA. And here the DSC range, which shows as 157 degrees centigrade, sharp endothermic peak, which we can see it as 200 and 287 degrees due to the loss of lattice water, which we can observe here as sharp peaks, which we can observe here at 287, and we can observe this one as different peak lines as 200 to 287. Right? And due to the loss of this lattice water and decomposition of this compound respectively, which shows the conformation of melting point and doped crystal is present in the 287 degrees centigrade. And the shifting of this peak towards this higher temperature, we can see the doped crystal is present or not. And the crystal variations can be observed towards this doped and non-doped crystal, right? And coming to this other analysis as SEM and EDAX, we can see is a SEM micro-analysis. We can see this, we are naming it as scanning techniques or scanning analysis, of which we can study for this. And the surface morphology of iron doped and manganese eliciting crystal, which we can observe this one as the presence of elements iron doped with manganese, the sample grown, which we can see energy dispersive, we are naming it as EDAX, energy dispersive X-ray analysis. We can see the variation in the micro MMs. We can see observe the values of these two different patterns of the SEM and EDAX studies. We can observe this one as the particular iron is doped in the manganese. And we can here we can see this micro hardness studies also. Micro hardness is particularly estimated for this. The particular is present in the hard material or not. We can see in the normal words as. That means the hardness of this. So when we break up this material or the crystal which is formed, it is particular pressure, at a particular pressure it should be broken. And the particular hardness of this material, it should also be measured. And we can see the transparent polished crystal free from cracks are selected hardness measurements. We can see the 25 to 100 grams and load ranging that is of. And we can see identification of this kg per mm square. We can observe this one as with the different formula ranges, as we can see hardness is 87.5 kg per mm square with an applied load up to equals to 100 grams. We can observe this one as the value increases with the hardness range. And we can also see above the 100 grams load, cracks were formed due to the release of internal stress. So when I apply the pressure on this particular crystal, we can observe the crack orientation depending on the hardness of the particular crystal. Any crystal which shows this micro hardness technique, which shows the analysis, which shows us the studies, which gives the hardness strength of a particular crystal. If you apply the pressure, depending on the pressure, it will be the crystal hardness can be valued. And the variation of this micro hardness is applied load, which we can see it is iron and compared to that of manganese, which we can see the difference of this. And we can see, observe the image of this and micro hardness range. And at a particular 50, we can see it as peak and as of 100. And we can see the load applied here in this, and in the we can see how much applied load 100. We can see this 85% hardness we can observe, right? So up to the 100 grams, we have applied the load, and we can observe the hardness HV value as 85. So with this also we can see that as the particular crystal formed as hard or material is hard or not, we can observe. And we can see the chemical etching studies as another one technique we can see it as. And the chemical etching studies which are carried over the growth of this iron, as we can see, this one is cracked. The material which is of grown doped manganese crystals were subjected to etching with water. Etching is nothing but we can say subject oriented with this salt or not. It's a dissolving technique we can name it as. The surface of this grown crystal were dipped for 10 seconds and 100 etching of the for etching technique. We can see this. The size of etch pit which is formed iron doped manganese elicited in hydrochloric crystals were large compared to the pure. And is attributed crystal perfection of this, and we can observe this one as the whole depth which is formed with iron doped with the manganese eliciting crystals is larger compared to that of pure eliciting hydrochloric crystal. Nothing but the complete addition of this another metal also can be observed for the future studies. You can see. And coming to this major one, there's NLO activities of iron doped manganese eliciting crystals. We can see it as is conferred by this crucifery powder technique. We are naming it as NLO non-linear optic studies. And the powder crystal was exposed to usage and the instrument name, we are naming it as ND laser beam of wavelength of 1064 nanometers with input energy of 8.8 millijoules of this pulse duration of 8 nanoseconds. And we can see it as repetition of this 10 hazards towards this spots is of 1 mm diameter is used in this technique. This is the technique which we are using for this NLO optics, which are for the powder technique. And the grown crystal was grounded with a fine microcrystalline powder where densely packed between transparent glass slides and microcrystalline sample of KDP were used for comparison of the conversion of efficiencies of grown crystals, which were named to the size of the wavelength of 1052 nanometers collected from the monochromator after separating the 1064 nanometers with input power of 0.65 joules per B. And we can see the SHREE deficiency as a harmonic growth, single harmonic growth of this efficiency of this iron doped crystals, which is found as 6.5 joules and higher than that of many organic and mineral crystals, is slightly lower the KDP for 8.8. We can observe this, that different variations can be observed this energo properties are present in this. And coming to this biological activities, which you can study this as iron doped with this biological activity, we can study, we have studied here as antibacterial and also the microbial activities, which is actually very essential for this for any type of crystals or as any type of material which we can in the research oriented. And we can see the antibacterial activity of the metal complexes tested with gram positive and gram negative bacteria. We can see it as gram positive. Some of this we can observe is Staphylococcus aureus, and Streptococcus pneumoniae, and gram negative we have Pseudomonas aeruginosa. We can see it as a bacteria as well as deficient method. And we can see this Petri plate technique we have observed here. Nutrition agar medium was prepared by this peptone, beef extract, sodium chloride, agar-agar, and distilled. These some different ingredients or different growth parametric techniques which we can observe for this biological activities. And 25 millimeter nutrient agar media which are poured in each Petri plates, and after solidification 0.1 ml of test bacteria spread over the medium are used for the spreader and were placed at 4 equidistant places at a distance of 2 centimeters from the center in the inoculated Petri plates. So this technique is, which we are naming this one as a Petri plate technique, which we with the agar-agar medium. And all determinations which are able to make this duplicate formation of this each and every compound, which shows that as Petri plates, a refrigerator of 24 hours, and which shows that as incubated for 26 to 30 hours with a temperature degree of 28 degrees centigrade. That is a particular of room temperature we have mentioned here, this Petri plates, and the growth has been observed. And these are some images we can observe here with different gram positive and gram negative bacteria. And the zone of inhibition, which we can observe this one as the round circles, which we can name this one as the inset of the middle one. We can see it as the compound, and the inhibition which is observed, we can calculate in the millimeters, and antimicrobial screening data, which we can represent this as in the table format of this next, and indicated as microbial properties. And we can see this one as how much it is inhibited, the zone, which we can mention the layers of this. We can observe the sensitivity of 3 bacterial species as Staphylococcus aureus and Pseudomonas aeruginosa. We can say Staphylococcus pneumoniae, and we can see different streamlines of the variations can be observed more and lesser and lesser. And compared to this, we can see here the zone of inhibition of these 3 bacterial strains. We can observe here Staphylococcus aureus and 13 as zone of inhibition millimeter, and we can see as of finder of inhibition MIC ranges, we can see minimal drug concentration levels, and we can see Streptococcus pneumoniae as 10, and as we can see this 485. And Pseudomonas we can see 11 and 375. These are different variations we can observe as depending on the bacterial inhibition range. And we can see this one as the bacterial is sequentially observed that the particular crystal format is not affected in a more range. Right? We can, from this bacterial studies, we can observe this one. And coming to the conclusion of this, as the manganese elicitin complex, which we can observe this one as the lattice, which is using the dopant, with its yellow colored crystals are formed, and iron 3 Fe3 plus ions doped with the manganese elicitin chloride with dimensions of 12 into 10 into 4 mm. That we have slow operation technique. And with the powder X-ray, we can study this one as different P212121 parameters. We can observe this one. And EPR spectral studies, we have studied a G value as 2.0292 due to the overlap of spin lattice relaxations of manganese and iron suggests this distorted octahedral symmetry for iron ions in the host lattice. Host lattice is nothing but we name it as manganese L-histidine hydrochloride crystal. And for the shifts also, we can observe this FTR characteristic vibrational spectral frequencies as L-histidine is completely presence of this iron. And these are the characteristic transitions we can observe this manganese, iron, and UV visible spectrum. And we can see the DQ parameters and molecular levels and HSG activities of 6.5 millijoules. And we can observe this one. And coming to the next one, as this is of iron cobalt, iron doped with the manganese, and this one is the second one, as we have known this as cobalt ions doped with manganese. And in the place of cobalt, we have observed the previous one as iron, and this one is of cobalt. And cobalt doped also, we already published this one work as cobalt doped with manganese L-histidine hydrochloride monohydrate crystals. And with this, we can see the image of the crystal of the cobalt as this like this violet colored doped manganese L-histidine hydrochloride crystals. And with the maximum grown dimension, we can observe this one as 15 by 10 by 5. As of iron, we observe this as 12 by 10. And this is we can say bigger size of 15 by 10. And we have studied the same analytical techniques for this also for different order X-ray studies diffraction. And we can observe this one as ABC ranges. We can observe this one as for the pure and the cobalt. We can observe the different variations of this X-ray studies, EPR studies, and APR spectral studies also we have observed. And the G value of this we can mention is 2.0308. And we can observe the value variation can be observed compared to that of iron, cobalt, nickel, copper, zinc. And the future studies also have been completed as nickel, cobalt, and nickel, copper, and zinc. And we can see this one as EPR spectral studies and variation. We can observe this one. And coming to the FTR also, we have seen this one as different variations can be observed in the peaks and ranges of amine nitrogen present on one. We can see it as at the range of 1140 through 1133. We can see it as individual nitrogen ring. And in the case of this one, we can see it as 1110 to 1120. Right? We can observe the variation of this iron, cobalt, and particular transition metal ions which we have doping towards this manganese L-histidine hydrochloride, which we are naming as host lattice, which we will observe this one as the host lattice is completely supported towards this transition metal ions, which we have for iron, that is a cobalt or nickel or copper or zinc, whichever the metal which we are doping towards this, right? And we can observe the vibrational modes of this L-histidine hydrochloride and the cobalt ion doped. We can observe this one, different variations can be observed. And UV visible spectral studies also. You can see it as optical absorption spectral as 200 to 1400 nanometers we have studied here. And we can see the DQBC values as we have previously seen as DQBC values for these cobalt ions and manganese ions. We can observe the variations of this, whether it is doped or not. We can observe this one as variation of 375 and we can see it as 595. And this cobalt is doped in this ions, and this we can mention the differences. And coming to the iron, NMR spectral studies also proton and carbon. You can see it as C13 and proton NMR plays a major role that it is a particular organic materials are present in that organ. You can see it as proton NMR cobalt doped with manganese crystal. We can observe the variation as the tabular format is mentioned here. You can see pure and cobalt. We can observe the variations. And coming to this also spectral studies of C13 and also this C13 NMR spectral studies also we can see as delta value variations. We can observe this one as pure and the cobalt. We can observe this one as 176.86 for the pure L-histidine hydrochloride, and we can see cobalt and doped with manganese. We can see it is 172.34, and the variation can be observed here with the delta values of C13 NMR. And we can see the spectral information here. And for this mass information also, we can see this as 305.1. And we can see that no more variations of this as for this iron or cobalt. A slight variation can be observed. 3.1, 3.305.1, 305.2, slight variation of this due to the presence of the sequential manner of this transition metalines, iron, cobalt, nickel, copper, zinc. Slight severe variation due to this, that we can observe this mass spectra also varied with a slight mode of number. And we can see as the small variation in the molecular weight could also be an indication that molecular structure can be included in the impurity. And impurity was in the dopant, we can see name it as, right? And also showed the series of peaks as 156, 181, 203, and 256 of corresponding various fragments of this molecule whose intensities gave the idea of stabilities with respective fragments. And this all shows this as the variation of this different doped and non-doped are the host we can see. Elicited hydrochloride and also cobalt doped, or else iron doped, or else different metals. And with the thermal studies also, we can observe this one as different variations can be observed here. And the range of 288 to 375 degrees centigrade. And the decomposition of volatilization of the compound, we can observe this one. DTA techniques, DTA curves, we can observe here. And the DSC analysis also we can see here as smooth up to 157 degrees centigrade and two sharp endothermic peaks of 200 to 288 degrees centigrade were attributed to the loss of lattice water and melting point. You can see already seen that as first the primary loss of occurs here, it is water molecules. You can observe this one as 157 degrees centigrade. We have lost this water molecules and hence the stabilities of this, and we can see this pure elicited hydrochloride and also the doped. We can observe that variations. And here also SEM and DDAX analysis. And also we can observe this different ranges of this SEM studies. We can see microanalysis. We can see as the EDAX analysis also. We can observe this one as a confirmation of this presence of elements, cobalt ions, which are doped with this manganese elicited hydrochloride crystals and the sample grown crystals, which can resist energy dispersive X-ray analysis. And we can also see his micro hardness. And hardness is always, we can see it as, we can observe this on a maximum of 83.2 kg per mm square. And his applied weight is 90 grams. And compared to that of iron, you can see this. So each and every metal varies with the hardness technique, with and also with the whatever we can name it as hardness, and also this as weight of the particular crystal. And variation of micro hardness with applied load of cobalt iron dope, we can see observe the variation as 83.2 kg per mm square, and applied weight is 90 grams. And after 90 grams of load, HV value increase in the load value due to this presence of discussed. We can see it as the presence of this metal variations. And here we can see etching studies also, and etching studies are carried out on this cobalt and doped with this of pure elicited hydrochloride crystals. And these are some NLO activities we have studied, that is found to be 7.7 millijoules and towards a KDP value of 8.8 millijoules. And the biological activity also, we can see the images of this three bacterial nature. We can observe this sensitivity. We are naming it as Staphylococcus aureus, Streptococcus pneumoniae, and Pseudomonas aeruginosa. And we can see the variation of this micro inhibition, and we can see it as a range of this hard zone of inhibition of this three bacterial strains. You can observe this one as different streamlines of this different bacterial species which are affected, which are going to be affected towards a crystal nature. And these are some contributions of color contribution of 15 by 10 by 5. You can observe this one. And this is some point. And next one we can see nickel. And nickel cobalt, we can observe this one as nickel doped with the manganese elicited. And iron, cobalt, and this one is, third one is the nickel. And we can see already published this one on cobalt, we have published. And here we can see it as the crystal format of, we can see the different sizes, we can observe this one. Due to the presence of this nickel, the color variation varies. And the presence of cobalt, the color also got that. And iron, we can observe this one is iron. Depending on the metal which we are doping, that metal color reflects on the crystal also. We can observe this one. And the powder X studies also studied like this, and we can observe this one as ABC values of crystal of variation of different streamers. XRD pattern with the pure nickel and nickel ions doped with manganese. You can observe these three variations can be observed in the spectral information. And also this lattice parameters also, we can observe this one as the size of the spectral, the size of the crystal, we can observe this one as orthorhombic structure. And we can mention here as depending on the ABC values of a, which were named as lattice parameters of a XRD pattern of particular crystal or doped or non-doped. And we can observe this one as the experimental calculated data. We can see which is generated from the software, or in software we can observe it as, and also this XRD data information, also XRD particular software will be there, and then we can develop these indices of this to what's calculate the spectral changes and the spectral size, and also the shape of a particular crystal. And here we can observe this as IPL spectral information also towards this, and the G values also can be mentioned here, and FTR spectral studies also. The same spectral analysis is repeated for this. All the crystals, all the spectral information we have given for this towards this different transition metal ions of iron, whether it may be cobalt, or it may be nickel, or it may be copper, or it may be zinc. The 5 different streamlines of these crystals has been developed towards this analysis have been developed towards this different nature. We have compared with this different metal ions which we doped with the manganese eliciting hydrochloride. The host is the same, manganese eliciting hydrochloride crystal, and that is doping with the different transition metal ions, iron, cobalt, nickel, copper, zinc. And compared to the values of this, all this we can observe different variations can be observed. And UV visible spectral studies we can observe here as the nickel doped with manganese eliciting hydrochloride, as we can observe these variations of iron, nickel, and also the manganese ions. And we can see here 1090 towards this wave number of 9171 towards 9150, and towards this only manganese we can observe this as 425, and this 23523 we can observe this one as a variation of this manganese only in the host and also the doped. We can observe the variation of these values. And also proton NMR, we can observe this as the proton values, hydrogen values, which we can limit as H2, and we can say alpha beta values of this variation of this pure, and also the nickel ions doped with manganese eliciting hydrochloride crystals. And also the proton NMR image, we can see spectral information. So the main variation we can observe here as the imidazole ring, we can observe this one as the changes occurs in the NMR spectral data, and the hydrogens which are present in the proton NMR, which reflects the alpha and beta values of a particular doped and non-doped crystal. And the C13 NMR also we can observe this carbon molecules, we can atoms which are present in that, we can observe this one as what is side chain, CH of imidazole ring, and imidazole ring carbon, and CH of the side chain, and also you can observe this different observation variations can be observed with the pure and also with the nickel doped. And the mass spectral studies also we can see, and here we can observe this as 305.4. We can observe the variation of this iron and cobalt 304.1, 305.2, then we can observe this one at 304.4. We can observe the variations as increasing range of mass of shows that as a crystal is completely doped with a particular element. As we can say it as increased transition metal ion. The metal also shows that mass spectral with the mass spectral data that the metal is completely doped with this. The variation of this mass we can observe this, and peaks we can observe this 122, 195, 222, and 278. And we can shows that as various fragments of molecule which intensity shows that as respective fragments as that a particular transition metal is completely present in the eliciting hydrochloride crystal. And here we can see next one as thermal studies also. We can observe this one as the first weight loss, and also the we can observe the 4.8%. And also DTS studies, we can see it as 286 degrees to 372 degrees centigrade. And also we can see the loss of crystal, same the pattern of this week. We can observe this one as loss of water molecules and the metal point doped the crystal followed. And also DSC analysis, you can see 202 to 86 degrees centigrade, and smooth of 156 degrees centigrade, and two sharp endothermic peaks, we can observe 200 to 286, we can see it as two sharp peaks. And also SEM EDAX analysis, we can see it as a different analysis of this SEM and EDAX also shows that as confirmation of this particular micro test, we can observe this one as the particular crystal variations can be observed or not. And the micro hardness, here we can observe this one as 60 grams and 82.5 kg mm square at an applied weight of 60 grams. And after 60 grams of load, HV value decreased, increasing load value due to the same reason we cannot discuss the previous one. And etching studies also, we can observe this is 10 seconds, indicated that deformation of crystal was minimum in the process of etching and increase the time to as discussed earlier, we can see. And also biological activities of this, different inhibition techniques. And we can also observe here zone of inhibition as the three bacterial strains of 14, 12, 11. We can observe this as MAC values as 500, 500, 370. And we can see that variations can be observed in the different transition metal ions. And depending on the bacterial species, the growth inhibition, we can observe this. And coming to this conclusion, also we can see here as a 10 by 9 by 7, we can observe this as 45 to 50 days time duration. And depending on the days duration, the crystal size also varies. Sometimes it may be increased, sometimes it may be get on for this the size that the same whichever this is 10 by 9 by 7. That was the size will be stopped and it will not be grown as it is the days duration also. And particularly this slow evaporation technique is particularly maintained in the duration of the temperature range, room temperature range also. And but summer duration also, we can see now this is February and this is March, April month. This is the months which we can get the crystal size in a early time duration, which you can see 45 to 50 days. We can see it as we can get 30 to 45 days also, depending on the temperature range. Not with this of hot air oven or anything else, but at a particular room temperature and atmospheric, without any atmospheric or without any temperature pressure. And we can see the EPR spectrum as room temperature with the resonance of characteristic manganese of nickel, and we can observe this as 0.55. We get a significantly covalent bonding between the nickel ions and the ligands. Right, like this we have developed this cobalt also, and we can see the nickel and the copper. The same, we can see the images followed by the copper images. The color reflects the copper. The same powder extra analysis you can observe here. So like this we have studied different variations of this as different streamlines of spectral analysis of comparative studies of 5 transition metal ions. You can see here spectral data information of EPR, FTR, right, UV visible, we can see it as. And here we can see it as UV visible of 825, and we can see it as 425 for the manganese, and copper we can see it as 825. And proton also we can see here the 4.35 per thermalist reading, and we can see the 3.99. And see on proton and the carbon we can see variation. Right. So like this, we can observe this one as different variations can be observed towards this, towards the different metals and different work which we can going to depending on the metal ions towards the host material. And we can see this NLO and biological activities towards this different streamlines of this crystal growth, depending on the material, depending on the ratio which we are applying, and depending on the whatever we are getting for the amino acid. These all streamlines get together to form a crystal format. So we can see it as now we are going for this Raman studies and also single crystal XRD studies of this. We are going for previously we were studying for the powder X-ray studies. Now for single crystal XRD studies has to be developed now, and the dielectric studies and laser damage threshold studies. Some of the other studies also there we have to study towards this, and we are going for this for the future, right? And these are some list of publications we have done. Now we have developed and completed this. And thank you.
So thank you, sir.
Thank you, sir. Thank you, sir.
Uh, Very good noon to all. It's my pleasure to deliver a vote of thanks in this wonderful occasion. I express my deep sense of gratitude to the management for permitting to conduct this wonderful webinar. My immense pleasure to thank our chief guest, Dr. J. Sai Chandra, Assistant Professor, JNTHU University, Telangana, for his willing acceptance. I am sure that your lecture will empower our studies, sir. Thank you, sir. Thank you so much. I thank our principal, Dr. N. Sujata, ma'am, for her constant support and encouragement. I am glad to thank our head and Department of Chemistry, Dr. G.P. Bhawan, for arranging this wonderful webinar. I thank all my colleagues for the support to proceed this webinar in successful manner. I once again thank everyone for making for their support and their cooperation. Thank you, sir. Have a nice day. Thank you, sir.
Thank you, sir. Thank you.
Yeah. Sir, sir,
Sir, tell me, sir.
so one question from student side, sir.
Yes, sir. Yes. Yeah, yes.
How to identify Mach spectra?
Yes, yes. Okay. Is the mass spectra is completely varies on the metal which we have doped here, and compared to this as the mass which we can observe here as for the mass spectra we can name it. I will show the difference of this. So for each and every transition metal ion, it always depends on the elemental stage of this particular metal ions, and mass spectra always varies with the previous host material and also towards the doped material. And we can see here, I will show you the peak of this. C13. So depending on this molecular weight of a particular metal which we are creating, suppose it is of 300 approximately, we can see it as 300, and the mass which is present on this before the doped with metal doped before, we can observe this one as 300, and after this observation of this doped material, we can observe the complex material is the size or the weight, the molecular weight is increased or not. We can observe the slight variation can be observed. If it is 300 of this metal, we can observe this one as 302 or 303 or 304. We can observe the slight variation of this metal complex, so that we can observe that as the metal is the completely doped in the particular host. Like this, we can observe the variation of this mass ranges. Is it clear, sir? So in this, you can observe this 305 AMU, and corresponding to this very closely, we can observe this major species as 298, and we can observe this one as 305. And this one difference, we can observe this one as mass spectral identification can be observed. And depending on these peaks, which are a series of peaks, we can observe 113, 181, 2032, 222. And depending on these, the slight peaks, we can observe this one as the metal hydrogens or the carbon or any different types of elements can be present in that, and the atoms which are present in that, which can be represented here. The highest peak which can be represented shows that one as the complete complex element, and we can trans complex metal. We can observe this one as the difference of between this carbon atoms which are present in the complex and also the complete complex weight. We can observe this highest peak as the particular shows that one as the complex molecular weight, and that one is the molecular spectrum information. Is it clear, sir?
So thank you, sir.
So thank you.
Thank you. Sir, Bharat, sir?